Today we're going to talk about how to balance our small cat. Now, in the past few videos, all we've been doing is making sure that our cat can move its legs through a trajectory. All the motions of the limbs were planned. Now we're going to take a look at what it's like to build a closed-loop controller on a system like this. So, we have 2 degrees of freedom in our tail and 2 degrees of freedom in our head. That can allow the tail to sort of spin clockwise and counterclockwise around the body. And what that does for us is if the body starts to tip over like this pink arrow here, then the tail can spin in the other direction and provide a force to push the body back using the momentum of the tail spinning to affect the momentum of the body tipping so it doesn't tip over as much. This is pretty cool. Let's take a look and see how it works. Alright, so we have 2 indexes in the tail. We're going to pay attention just to the tail for the spinning. We have index 0, which moves the tail up and down, and we have index 1, which moves the tail side to side. Now the first thing that we're going to want to do is compute a delta time. And delta time is going to be sort of how far in the precession of the tail. The tail is spinning around, where in that spin is it? And the way you do that is you take a look at what time it is now, and you're going to subtract the last time the tail spun all the way around and got back to 0. If it's the first time, you just sort of set it to last time to now, so that as you move on, that this equation should just work. And what that'll do is give you a number. If you divide it by how long you want that loop to take, it's going to give you a number from sort of 0 to 1 that represents where in the spin that tail should be. Now we're going to do a little trick here, which is if the tilt is greater than 0, we're going to take our delta time and we're going to multiply it times -1. And that just means that the tail will spin either positive, clockwise, or negative, counterclockwise, based on the balance point on the body here. So, just real quick, I want you to see that when we talk about the body tipping, we're going to be talking about it tilting side to side like this. And the angle that we use to represent this is our alpha value, this value right here, which is represented as the angle of from the IMU, which is the tilt value, or I believe the elevation. Yeah, I believe this is the elevation value for the IMU, and it gives you a little angle from sort of upright over, and then once it gets to 90 degrees, it starts getting smaller again, and comes back to 0 at the other side. And so that value is going to represent from a unit value would be from upright to 90 degrees over is sort of 1 full times. That's what we're going to multiply as our gain value, is to turn that alpha into a unit vector. Okay? So now we have the sine and cosine for the tail. Let's take a quick look and see what that looks like. So, this is a example device that I'm going to be providing for you. And the first thing that we do is we're going to load our new class using Device Manager. Device Manager.get specific device, we give it the name, and we're going to expect it to show up down here. We're going to return new Physics Manager example. In order to be a valid device, it only has to have 2 things: a connect method and a disconnect method. The connect method, if it connects successfully, should return true. And if all those conditions are satisfied, then when you return an object with those 2 methods in it, it'll show up down here in connected devices. That's all it needs. It doesn't need a special interface, just needs to have those 2 methods. So, to do all of our math, we're going to have a runnable event. You can think of this as the thing that's inside of a thread that actually runs, and you can create instances of these sort of inline like this. Now, what we're going to do inside of our event, and this event is going to be called every time the IMU updates, we're going to start by grabbing our head and tail and storing them into variables. And every time the thread is called, we're going to know that the values inside IMU data, which are retrieved from the devices in the start of the class up here at the top, you'll know that the values in there have been updated. This event is synchronized with the thread that updates these values. So once we have a new tilt value, we're going to compute our sine and cosine values. I'm not going to show you that. That's the answer. And when you're done, you're going to set those new values to your head and tail. And so let's take a look and see what that looks like. So, as you can see, because Grace is tilting to one side, the tail begins to spin faster and faster. And we get back to 0. It'll stop. You start tilting the other direction and start spinning the other direction. And if we turn the servos on, the effect happens with the real servos. Now, that alone will give you a much better walking, but I think we can do quite a bit better than that. Let's take a look. So now that we have our closed loop controller running, let's see if we can do better by statically computing tail values. So tail value here or here, and a head value to this side or that side. That will move the center of mass to the cat's right or to the cat's left. Right, left. So we're going to compute some values for these head and tail so that the cat's center of mass will be between its 2 feet. Let's see what that would look like. So, we want to put the center of mass on the line between the 2 feet. So, this line represents where the cat is balanced. If the center of mass is on the line, then the cat is balanced. Now, to start with, we might not know, might not be in the condition where the center of mass is there. But if we move the head and tail around, we can sort of adjust the center of mass and move it towards that point. So in order to do that in code, we're going to need a couple things. So the first thing we need is this beta value. Now beta represents the angle between our tipping line and the robot fiducial's y vector. So the reason we care about the y is because we know we're going to tip from our sensor is aligned with that y vector. So we know we're going to be tipping along according to the sensor value that we are reading. That's the tip line that we care about. Now, to get that beta value, we just do a tan 2, the front foot x minus the rear foot x, and the front foot y minus the rear foot y, and that gives us our beta value. The transform is simply taking the beta value and applying it as the azimuth of the rotation. So that's the sort of rotation about z, the azimuth, and that's the value that we're going to set beta to. Now, we also have another transform, which is the location of the rear foot, but just the x and y value. We don't want, we're going to set z to 0, because we're just looking at the projections in the xy plane, and we're going to use no rotation because we're just dealing with the position of that support foot, not the pose of the foot. Now, if we multiply these two transforms together, we get the transform of the tilt plane, and this is useful for our next piece of math. So, before we get to that, we're going to have to compute the center of mass. So the center of mass is simply a rolling sum of the x component times the mass, the y component times the mass, the z component times the mass of a particular link, And then you're also going to sum up the total mass of the system. Now you are going to want to make sure and exclude the head and tail from this center of mass calculation, because it's an incremental center of mass. We're going to set values to the head and tail to sort of tune it from there. But we know the center of mass of the rest of the system, so we're going to compute that right away. And if we have those component values and the sum of all the other masses, we can move on to the finding balance. So finding balance is a for loop where we're going to iterate over every possible value to set to the head and tail. So basically we're going to read scale and iterate from lowest bound to highest bound with the increment of scale, which is about 0.5 if you took a look at the config file. That will give us roughly about 180 values that it's going to sweep through. So it's not that many. It seems like it would be a lot, but it's actually not that many. Now, for each one of those values in between, we're going to compute the head and tail components from the head and tail components for the center of mass. We add them to the component center of masses that we computed for the rest of the body, and we get a new transform, which is this transform of the head and tail center of mass. And we're going to do this 180 times and try all the different ones. When we compute that transform, we multiply it times the tilt transform that we computed earlier, and we're going to check the y value of the resulting component in tilt space to see if it's less than some minimum value, which in our case, let's say a millimeter. That means the center of mass now is within a millimeter of the support line. So we just go ahead and store the pose and move on. We break from the for loop once we find a value that's within the minimum, or if you get to the end of the for loop, you just store the best value that you had, whatever was closest. Note that the head and tail, based on the way they're configured, they're going to be negative from each other. So a value for the head will be sort of negative of the value for the tail. So make sure you're using that for your computes. So the head moves off to the head and tail both move to the same side at the same time. Now, how do we add it all together? We take a look at our compute for the sine and cosine values from before, and we're going to add to that a tail pose for the tail, and then we're just going to set the head to the tail pose times -1, which means the head and tail are both being set, and the tail has two components, the sine and cosine values and the tail pose. Those two added together give us our total pose. So let's take a look a little bit and see how this will find its way into the code. So inside the physics manager that you're going to build, you're going to have an update pose function, and that update pose is going to get the feet touching the ground, and you can either gate it here or you can gate it in the event, just to make sure it doesn't run faster than 20 milliseconds, otherwise you'll get ahead of your screen and bog down the computer. Compute your tipping plane, just like we said. Then you compute your center of mass. Then you find the angle for the head and tail that brings balance. Cool. And if we want to take a look and see what that looks like, let's look at the center mass following along the vector. Good. Takes a couple steps, and the head and tail move to keep the center mass on the line. The yellow square representing the center of mass. Great. Well, now let's take a look see what that looks like in real life. Alright, I'm going to run the script. Cool. Awesome. Alright. You now have the ability to balance your SmallKat with a closed-loop controller and compute the head and tail locations to keep your SmallKat balanced in a static balance system. Thank you for watching.